Good morning to all our colleagues here in the US, and good evening to our colleagues in India. Thank you again for joining today's seminar. Believe it or not, this is actually our 15th seminar in the joint webinar series between Binghamton University and VIT. Over the last few months, we have accomplished quite a bit with many speakers from both Binghamton University and VIT, talking about various topics related to advanced manufacturing, material science and engineering, additive manufacturing, and many more. And today we are delighted to have Professor Scott Schiffres from the Department of Binghamton, from the Department of Mechanical Engineering at Binghamton University. Professor Schiffres is an assistant professor of mechanical engineering at Binghamton University. He was a postdoctoral research associate in the group of Dr. Evelyn Wang and Dr. John Hart at MIT before coming to Binghamton University. He received his Ph.D. from Carnegie Mellon University, where he was advised by Dr. Jonathan Mullen. Scott worked at Boeing Satellite Development Center for 2 years before going back to school for a Ph.D. He received his bachelor's degree from Princeton University and Master of Engineering from Cornell University. And most recently, Dr. Schiffres received the 2019 National Science Foundation Career Award. So we're delighted to have Professor Schiffres with us today to talk about 3D printing for enhanced electronics cooling. So Professor Schiffres, I will hand it over to you. Scott, you are on mute. Yeah.
Okay, can you hear me now?
Yes.
I don't want to give the whole seminar on mute. So you might hear some acoustical disturbances. I think I heard my kids waking. But we'll see what happens there. So I'm not actually in our lab at Binghamton. This is just a realistic background of our metal 3D printer. So today I'm going to be talking about enhanced electronics cooling by printing onto silicon. And this work was done largely by, the work that I'm going to be discussing was done by my grad students, especially at Rod. I'll be talking about Rod's work, Jake's work, and Mateus's work in particular. So let's get started. So one of the main topics my group looks at is how we can cool electronics better. And in this talk, I'll be discussing about 3D printing onto silicon as one way possibly to do this. But we're also working on other research areas as well, like the thermal properties of thermal interface materials. We're also looking at adsorption that can harvest waste heat more efficiently, and looking at applications of 3D printing to heat transfer. But I'm not going to go into detail on all these topics. So why are we interested in cooling electronics better in the first place? So this plot here shows the power of microprocessors versus year. And you can see there's a trend line here of about 7% growth per year in processors for servers and GPUs. And if we look at a processor, you might have heard of cores before. I know it's a diverse group, so with all different engineering backgrounds. But cores are basically like pistons on your engine, or cylinders on your engine, right? If you get a 4-cylinder car, you expect all 4 cylinders to be running when you drive it. With microprocessors, you might think that it should be the same way, right? If you get 24 cores or whatever, how many cores you get, you expect that you have all those cores running simultaneously, but it's actually not the case. So how many cores are actually running at a specific time is thermally dependent. So as one core starts to warm up and get too hot, maybe depending on its heat load and its neighbors, that core will turn off and the computation will move to a different core. And so if you actually want to get more out of your existing silicon, you want to cool them better. This is the so-called dark silicon problem, where you have transistors on your silicon chip, but you can't use them all at the same time. If we look at a chip here, so this red is a flip chip, and the heat is generated on the bottom of the flip chip where the transistors are. If we look at the path the heat has to take, most of it travels up into the heat sink. So the heat sink's eventually cooled by air or water, or there's other fluids that can be used as well, but it's eventually put into some fluid and into the ambient. But before it gets that heat sink, And you might have, if you ever built a computer, you know, the big heat sinks are these blocks of metal with fans on them. Before it gets to that heat sink, it has to pass a number of layers. And one of the first layers it has to pass is called a thermal interface material. So if you have a 1 centimeter squared chip, your approximate thermal interface material resistance is going to be 0.05 Kelvin per watt. So if your chip is outputting 100 watts, like it was maybe 5 years ago as an average heat flux, your temperature difference across the thermal interface material would just be approximately 5 degrees Celsius. You know, in the scheme of things, from the temperature the chip is at 80 C to ambient temperature, 20 C or 30 C, 5 degrees is not a huge issue. It's not dominating resistance. But as chips want to increase their heat flux to 500 and 1,000 watts per centimeter squared, this temperature drop across just the first thermal interface material can become significant, going up to, you know, as large as 50 degrees if you really were to increase to 1,000 watts per centimeter squared, as some hotspots are currently. So there's a big push to get lower the resistance of the thermal interface material, and one proposed way to do that is going to be printing onto silicon. But before I go into that, I just want to maybe look at some motivation. So for a lot of researchers, especially in industry, have been looking at embedding cooling constants. So this is a very promising technique from IBM, where they micro machine silicon microchannels. This is a top view of the design. They micro machine using photolithography techniques, microchannels, and they basically have coolant flow through the center of this hole, and then that coolant boils as it flows radially outward from that center point. So this is a promising technique to print, but there's some limitations to this silicon micromachining technique. For one, it's kind of complicated. It requires silicon photolithography, which is not cheap. Another issue is there's a practical limitation to how deep a trench you can etch. It's a slow process. Another issue is the thermal conductivity of silicon, while good, isn't quite as good as copper or some other materials like copper or silver. So our concept is basically to achieve similar kind of features as this direct silicon bonding microchannel cooling, but using additive manufacturing to do that. So my student Rod's been working on this, and the basic concept is that we could print little microfins or a sinter to help boiling on top of a chip, and use this instead of silicon to make direct cooling microchannels. So just a little background on what selective laser melting is. I don't know if everybody's heard of it, but let's say you want to print a castle. The way you would do this is you would deposit a thin layer of metal powder, just a hair's width thick, onto a build platform. Then a laser would come and melt the metal powder where you want the part to be. So the first layer would be the base of the rook. And then the build platform would move down 1 layer height. So that's about a width of a human hair. Another layer of powder would be squeegeed across the platform. And then the next layer of metal would be melted and fused to the layer below it. And this process repeats until the whole part is built. So it's not you know, depending on the size of the part, it could finish real quickly if it's not very tall. But if it's tall, it could take quite a bit of time. So it depends on the height of the part. Now, what if you just try to print metal directly onto silicon? Well, this is kind of a naive attempt, and you see that there's very poor bonding. This was printing aluminum onto silicon. This is silicon wafer here, and you can see at the corners that these squares have delaminated. And the reason for this is that there's the aluminum melts at a relatively high temperature, and it also has a coefficient of thermal expansion mismatch with the silicon. Most metals have much higher thermal expansion than silicon does. So these two things make it hard to print metals onto silicon. So our approach to try to print metals onto silicon is to first use a low melting point solder alloy. And this is to reduce the driving temperature difference for thermal expansion mismatches. Right? The thermal stress is going to be a function of not just the mismatch, but also the driving temperature difference of that mismatch. So if we can use a low melting point alloy, that'll reduce the thermal stresses. And then to that solder, we want to add an element that'll form a reactive bond to silicon and form a particular silicide. So we chose to use titanium mixed with tin silver. So it's like a tin silver lead-free solder plus some titanium. So there's some challenges with printing, creating a good bond onto silicon with laser 3D printing. In conventional brazing processes to dissimilar materials, like metals onto graphite or metals onto silicon, the bonding process takes on the order of minutes. But in selective laser melting, each pixel, each little area on that print is only hot for a fraction of a second. So can we really create a good bond in that small time that the part is heated up, that each pixel is heated up? So we mixed up tin silver titanium powder, and we've tried a few different processes for doing this, but this is a heterogeneous mixture. We bought tin silver and titanium and mixed it here. We've also done ball milling to alloy the material, and both have worked. So now I'd like to show you a video of the print process. I'm gonna stop sharing momentarily and see if I can do this, and then switch to video. Can everybody see the video screen? I'm gonna change the settings so it's optimized for video here. Okay, so I'm gonna turn this video on here. How can I do this? Okay. Okay, so I'm gonna run the video. So let me just explain what we have here. So this is a silicon wafer, and it has a thin layer of tin silver titanium powder deposited across the surface. So when we go to laser raster it, this is our first laser exposure. And you can see the metal is kind of shiny, but there's some dullness there. And then we're gonna do a second laser exposure of that same area, and it's gonna become a lot more shiny and metallic. Okay, so let me go back to the slideshow here. Okay, now how do I show? Okay. Okay, so sorry, there's a setting here I have to change. It's asking for my password for something. I don't know what. Can everybody see my screen? Can everybody?
Yes, we can see it, Scott.
Okay, thank you. Yeah, sorry, I don't know my.
Yeah, no problem.
Okay, so we just saw how we could print onto silicon. We printed a Binghamton logo here because for school pride, but so these are some other prints that we've done. So this is printing a Binghamton logo onto silicon wafer. So we printed basically in this example here, we printed a few hairs width of tin silver titanium, and then on top of that we printed stainless steel. If you're a heat transfer person, you know stainless steel isn't a great thermal conductor, and the reason we used stainless steel at the time was basically because our printer had that, and we weren't able to change the powder quite yet at the time. We've since printed on aluminum as well, and have had good results. I'll show some of those a little bit later. So this is a general process for how we could print onto a packaged chip. So we basically mount the chip into a holder that mounts the part, and then we tape up the side so powder doesn't get into the ball grid array and the solder ball array. And then we print a few layers of this tin silver titanium interalloy, and then print our other material. In this case, we print aluminum on top of that. This is showing that we could print very narrow. These are 400 micron diameter pin fins that are 8 millimeters tall. So it's a very high aspect ratio that we could do. We've also printed a lattice structure. So this is a lattice structure that we've printed with 1 millimeter struts. And this is a wick that we've printed as well. We can print wicks. And this is a microscopy image of the interface. There's some artifacts here from the polishing. These lines here are from the polishing. So this is another demonstration that we just got working recently. This is an Nvidia AI chip, and we just printed this lattice structure here. And we're in the process of doing some reliability testing of this. We had to actually desolder some of the components. We're kind of learning. We're learning how to do this on this chip. We had to learn some desoldering techniques, which was a bit of a learning process. So if we look at the cross section of this print, we have here in blue, there's silicon, and then this is kind of gray here is the interalloy tinsel or titanium, and then above that is aluminum. So this is, and then this is aluminum here. So here's some sort of intermetallic that forms between tin and aluminum. Okay, so here's some microscopy images of the interface. So here we have silicon. So these are elemental maps. Each one of these colors represents a different element. And so here we have silicon on this side, and we can see that some of the silicon is diffusing into the metal alloy. And most importantly, we see titanium. So there's a kind of diffuse cloud of titanium everywhere in the metal alloy, but you can see there's kind of a brighter region of titanium near the silicon interface. And we think that this is titanium silicide. It looks like it's about 1 micron from this electron microscopy, the scanning electron microscopy image, but it's actually quite smaller, we think, because electron microscopy has a rather, this technique, elemental mapping technique, has a relatively large interaction volume for SEM. So we can't really resolve how small it is. We have done transmission electron microscopy. So my colleague, Professor Zhou, and his grad student Xiaobo did some transmission electron microscopy, elemental mapping, and this is the interface. So this was on a slightly different material system. This was on carbon that has the same metal alloy printed on top of it. So this green here is the carbon layer, sorry, the carbon film. Excuse me. Okay. Nobody can catch it from the computer, fortunately. Okay.
Bless you, Scott.
Thanks. Feeling worn down, I think. I've been staying up too late, lately getting ready for the semester and proposal that's due. So here's the titanium layer that formed at the graphite interface. So we think this is a titanium carbide film, and the high resolution TM here we can actually see. So here's polycrystalline graphite, and here's the tin tie face, and in between we could see some crystalline Moore patterns, and we think that this is basically titanium carbide that's formed at this interface, because if you look at the titanium intensity, it has a peak about 10 nanometers right at the interface. So we think that a similarly thick layer also forms for the silicon, and having a very thin titanium silicide or titanium carbide layer, we think is mechanically advantageous, because it's that those kinds of materials are relatively brittle. So making them thin will make it more compliant. So next we wanted to measure the thermal properties of these printed materials. So to do that, we use a technique that we have in our lab called frequency domain thermoreflectance. And this is a pump probe laser technique. Basically, we use a modulated laser, this blue laser, to hit our sample. So this is a microscope objective, and it gets focused to about a 3 micron spot. We have several objectives, but the one that we use now gets focused to a 3 micron spot. And that's basically periodically heating that little point. And if we look at what's happening, this is the laser flux in blue. If we look at this, we'll see that the temperature response of that same point is also sinusoidal at the same frequency, but it's slightly phase shifted. So there's some lag. The max temperature comes a little bit after the max heating. And this is analogous to, this max heating on Earth is around noon. And then, the max temperature might be around 2 or 3 p.m. So this phase lag between the max heating and the max temperature will actually indicate the thermal properties underneath the material. And depending on how fast we modulate this laser, so the laser is turning on and off periodically, depending on how fast we do that, the thermal wave can penetrate just a short distance into the material. So we can measure very local properties. So you might not have to do this in India, but in the US, we have to worry about pipes freezing in the winter. So we have to bury the pipes a certain distance underground, and the distance that you have to bury it is dependent on this thermal penetration depth. So you can take the seasonal frequency of the seasons and calculate how far these thermal waves from the seasonal variation will penetrate into the ground, and that's how you could decide how deep to bury your pipes. So here's the raw results from this technique for a single point. So this is the phase difference between the heating and the temperature response versus frequency. And then we fit this, the black dots are the data, and then the blue curve is a fit to analytical model. And so we found that the thermal conductivity of this tin silver titanium alloy was about 40 watts per meter Kelvin. So that's about half of what tin is by itself. So we think we can improve this a bit. But even still, it's because we can print a very thin layer of it, we can basically have an interalloy that's about an order of magnitude smaller than conventional indium foil, which is already a quite good tin. This is a little bit on the thermal penetration depth, but I'm going to pass over this for the moment. Another thing we've been looking at is how we can optimize the design of the cooling fins and the manifold that delivers coolant to balance the competing effects of thermal resistance and pressure drop. So my colleague, Professor Samakia, and his postdoc Shrikant and graduate students have been looking at how to optimize the shape of these fins and the manifolds to enhance cooling. And we showed that we can cool 1 kilowatt with only a 46-degree temperature rise. This includes the TIM and everything, not the TIM, but the printed interlayer and everything like this. So I think that this is quite promising. We also wanted to study the reliability of the chips after printing. So we put a thermocouple underneath the silicon wafer and measure the temperature profile. Underneath. And we found that the temperature rise was less than 250 C on the bottom. So we think that this is quite reasonable considering other processes like soldering occur at similar temperatures. We've also done simulations. We've done more. These are some simulations that we did a while ago. We've since done some more complex simulations that take into account surface tension and various other effects. But this basic model shows that if the thickness of the silicon is typical of a silicon chip, 30 or 50 nanometers, that the temperature rise on the transistor side is not overly large. We've also looked at the mechanical properties in collaboration with Changhong Ke and his team. And one of the things that we found that was quite interesting is that when you try to shear off little pins that are printed onto silicon, the strength, we found that it didn't break at the silicon metal interface. It's actually sheared inside the tin. So this shows that the bond is actually quite strong between the tin alloy and the silicon. We've also done some basic thermal cycling tests. There's still a lot remaining before this could ever be used in practice, but we're still doing more of this. But we did 100 cycles with this Binghamton logo, and it didn't break off. At least we have to do more testing though. So just to summarize this printing onto silicon project so far, we've shown that we could print fins onto silicon, and that these can have lower resistances than conventional metal TIMs, even that are kind of the best performance on the market now. We also have been looking at how to optimize the cooling geometry and topology of heat sinks, as well as looking at the mechanical properties, so we can actually use this in a real device. And now I'd like to talk about a few other topics in the second half of my talk. So they're loosely connected to printing onto silicon. So when we print this tin silver titanium alloy and then print copper, which we haven't done yet, one of the things that will form is copper 3 tin. So the next part of the talk will be on copper 3 tin And this material is useful for a number of other applications. And then we'll look at the thermal properties of 3D printed metals. So copper 310, as I mentioned, is going to be present when we print this tin, silver, titanium alloy onto silicon and then print copper on top of it. But it's also important for other applications. So all of our cell phones, I don't know where mine is at the moment, and our computers have copper 310 inside of them. So solders contain copper 310. And next generation integration schemes may be made purely of copper 310 intermetallic bonds. So there's going to be 3D stacking of chips. And one of the things that's anticipated is that pure copper tin intermetallic joints may be formed. In that case, copper 310 will be a rather thick layer. So nobody, even though this material is quite important, there's never been any thermal anisotropy measurements of this material. And the only anisotropy transport measurements were of electrical properties of a liquid phase electroepitaxy, which showed a very high anisotropy of about 3. So we wanted to know, does that really apply for more conventionally made copper 310 joints as well? So what is copper 310? As an undergrad, you probably learned of solid solution alloys if you're a mechanical engineer. And this is a crystalline material where elements A and B randomly occupy different lattice sites. So this red and blue atom, they could switch places and that would be fine. And these kinds of solid solution alloys are what we normally think of as alloys. And they can exist in wide ranges of stoichiometries, of ratios of the two elements. Intermetallic, on the other hand, is also crystalline, but each lattice site is either occupied by element A or element B. Whether it's element A or element B is prescribed. So this is a picture of copper 310. And you can see that it's very crystalline. There's no randomness to the structure here. And because each lattice site is defined as being for atom A or atom B, these materials exist at relatively strict stoichiometries. Copper 310 is also a hexagonal close packed metal. If you look at this, you can kind of see the hexagonal tiling here, this honeycomb shape. And hexagonal close packed metals, these are from simulations primarily, but they have a wide range of anisotropies for the in plane versus through plane connectivities. And so as high as, actually I need to update this. There's iron at very high pressures that's been measured also that have been high as 4.5. Scandium is kind of the highest for pure metal that's been found, and that's over 2.5. And cobalt is relatively low. So the anisotropy of HCP metals can be quite large, but nobody's ever really looked at copper 310 for its thermal anisotropy. And so that's one of the things we want to look at here. So how do we prepare copper 310? So you may think it's pretty easy. We just mix 3 parts copper and 1 part tin, melt it, and then cool it down. But there's a little bit of a trick that's required. So if you melt it and cool it down just in a furnace, you'll pass through this gamma phase, and you won't end up with pure copper 310. So the way around this, we got help from Professor Eric Kotz in physics, and we used an arc melter. So this arc melter allows us, it basically, I'll have a picture on the next slide here. It's basically a welding torch that's in an inert environment, and you put your metal powder, your metal on this copper liquid cooled hearth. So it allows you to melt and cool the sample really rapidly because it's basically liquid cooled hearth. So we did this, and then we did XRD, and we could confirm that we have pure copper 310. This is a polarized light microscopy image, and because the optical properties of the metal are different in the different orientations, this microscopy image shows the different crystal grains as different colors. This is a polarized light microscopy technique. So we measure the thermal conductivity of this material as well. So I won't repeat how this technique works. And one of the things that we were careful to do when we did this mapping technique is we were careful to use frequencies that are high enough that we're measuring in a single grain of the copper 310. The grains were about 500 microns in diameter, in average size. So here's the thermal conductivity map. You might not be able to see my mouse because it's red on red here, but you can see that neighboring grains can have quite different thermal conductivities. So that's this red and yellow here. So red's low conductivity and kind of yellow is higher conductivity. You can see the crystal orientation is different from this polarized light microscopy image, but you can't use the color of the polarized light to tell you the, the crystal orientation. But you can tell that's different. So
Your voice is breaking.
Oh, sorry. Can you hear me okay?
Yes, I can hear you.
Okay.
Yeah.
It's okay.
Maybe I need some water. I'm not sure if it's the internet or my actual voice. So we did this thermal conductivity map, and these black lines in between are just to guide the eye at the grain boundaries. So for each one of these grains, my student basically made an outline of the perimeter of it and used that to do some analysis of the thermal conductivity over that grain. So we were able to get the average thermal conductivity and standard deviation for each grain in this image. So here are two representative ones. Now there's another feature of copper 310 I didn't mention before, but it has an anti-phase boundary superstructure. So if you look at this image here, if you can see where my mouse is, there's a line of a mirror reflection here about where my mouse is moving up and down. So in the B direction, in this direction here, going left and right, there's every 8 or 10 unit cells, there's a mirror reflection. In the literature, both tenfold and eightfold superstructures have been observed, but not together. So if you make a sample, it's either all tenfold or all eightfold that's been observed in the literature. So from the XRD, we could see that we have tenfold, this tenfold superlattice that is formed. So based on certain peaks here, the ones that are highlighted in green are peaks that are unique to the eightfold repeating structure. So we can see that we have this tenfold structure that's emerged. Next, we want to see how the thermal conductivity correlated to the crystal orientation. So we used a technique, a diffraction technique called electron backscatter diffraction. And this technique allows us to see the orientation or to measure the orientation of each crystal grain. So the colors here represent different crystallographic orientations of copper 310. So you can see that these two neighboring grains that I focused on before, 15 and 62, have different orientations. One thing you might also notice is that there's a little bit of speckle in some of these grains. So we also did transmission electron microscopy just to confirm what we saw was correct. So we looked at these two grains, 15 and 62, with transmission electron microscopy, with help from the ADL, particular Dr. Intebe. So this is grain 15, and this is the side view. So we did something called focused ion beaming to make a little fin of copper 310, and then we put that fin inside a transmission electron microscope and looked at it. So this is a high resolution TM map. You might see kind of striping. You see that there's kind of there's a pattern of stripes vertically. Well, this is actually the tenfold superlattice that we can actually see through TM images. So I think this is quite amazing that we can actually see, this extremely small pattern in the copper 310. So this tenfold pattern matches our XRD expectation. And then also the orientation of the crystals also agreed with our electron backscatter diffraction orientation. So we did this with 2 grains to confirm, and both gave close results to our EBSD measured orientation. So next we took each one of those measured thermal conductivity grains and plotted it on this 3D plot. So each one of these points here represents a grain, and the distance from this point to the origin is the magnitude of thermal conductivity, and the orientation the orientation from the origin is basically the normal surface for that grain in the ABC coordinates. So we could see that the thermal conductivity in the C direction was the largest, and in the A and B direction, they were quite similar, about 58 or 59 watts per meter Kelvin. So actually the anisotropy that we saw from, I was expecting that we might have much lower conductivity in the B direction, because that orientation has this tenfold superlass, but we didn't see that. And our colleague in physics, Professor Alexei Komogrov.
What does C represent?
Oh, sorry. Sorry, Dr. Bukpalan. Oh, can you say it again? Okay, so maybe a straight microphone. Okay, so why do these long-range antiphase superlasses form? That's one of the questions that we had, and it hasn't been addressed in the literature. Ernesto did some simulations of different periodicities. So they were limited because DFT is very computationally intense calculation. So they did a case of no superlattices, a superlattice every 4 unit cells, a superlattice every 2 unit cells, and a superlattice every unit cell. And they found something surprising. The minimum energy was actually for the unit cell, for the case of a superlattice every unit cell, called this D019 structure. So that was surprising, because in the literature, the tenfold or eightfold structures has been observed. Although there is one TM study that did find this as the lowest energy grain. So why we're not getting the lowest energy structure simulated by DFT is not really clear to us. Another thing that emerged from this density functional theory calculation was that the stoichiometry of copper 3 tin for these different superlattices wasn't exactly 3 to 1. It was a little bit copper rich. And so next we want to compare the anisotropy ratio that we measured experimentally to the anisotropy ratio that Alexei and Ernesto simulated with DFT. So this is our experimental anisotropy. So each one of these colors represents an anisotropy in a different direction, normalized by the Z conductivity. And so we see that for the experiment, we had anisotropy about 15%. The simulations had a similar degree of anisotropy, about 15% or 10%, depending on the orientation. So it's quite interesting. The only prior transport measurement that's been done on copper 3 tin was liquid electrophase epitaxy, and that has a very fast cooling rate. And our samples were annealed. So I think there might have been some microstructural difference that led to very high anisotropy for that prior measurement that's in the literature. But they didn't include any microstructure in their paper, so we couldn't really directly compare our properties to theirs. So to summarize this copper 3 tin work, we made the first anisotropic thermal conductivity measurement of this material. And we found that antiphase periodic boundaries had only a modest effect on the anisotropy. And this was also, I didn't mention this, but this is also a relatively new technique, being able to map the thermal conductivity, then relate that to the orientation dependent thermal properties has only been done once before in the literature, as far as I know. So, so this is also a quite novel technique. So finally, I'd like to also discuss the thermal properties of printed metals. So we're trying to make heat sinks ultimately. So the thermal properties are very important. So far we've studied the thermal properties of stainless steel, and we're almost done studying the thermal properties of aluminum, but it's not quite ready yet to share. I'm not sure if you hear my kids in the background. They're shouting in the hallway. But because our printer had stainless steel on the time, we've done a study of thermal properties of stainless steel. So that's what I'm going to be discussing next. So there's been a lot of work before on the mechanical properties of printed metal parts. I know at Binghamton, for instance, Dr. Fuda Ning has done some very nice work on the mechanical properties of printed metal parts and their fatigue life. Okay, I have a visitor. Okay, and their fatigue life. But there's been very little work in the literature on how the thermal properties of metal printed parts change with print processing. So when we print with our machine, we could tell it how much laser power to use, and we can also tell it how fast to move that laser over the part. So typically we operate at 200 to 400 watts, and the laser moves at maybe 1 meter per second. For typical metals on kind of that order of magnitude. So one of the things we want to look at is how the melting process parameters change the thermal properties of different metals. And so this stainless steel work was led by Jake Simmons. This was his master's thesis, and my PhD student Arad was also instrumental in this work. So we printed samples in our metal printer in two different orientations. So we printed through plane test samples and in plane test samples. So these are the in plane test samples and through plane. And we want to measure how the thermal properties change with orientation as well as with process parameters. So each one of these squares was printed with a different laser scan rate, and we held the laser power fixed at 200 watts. So here's a plot of porosity versus laser scan rate. So at faster scan rates, we start to have high porosity. So this is too fast a scan rate. And what we get is incomplete melting. You can see here that there's some regions that are not fully fused together. We go to faster, so when we go to slow down the laser, we start to get less porosity, and there's kind of a plateau here around 750 to 1000. This is kind of the machine spec process parameters for stainless steel. So if you print stainless steel with just the EOS default parameters, it'll be around here. If we slow down the laser even further from 750, if we slow it down another step to the left here, the prints will fail. And actually, I'll just go back one slide. You might see that there's some stubs here on this build platform. So these are parts that failed because the laser was moving too slowly. And if you move the laser too slowly, what happens is you're actually boiling a lot of the metal, and that leads to splatter. Just like if you're boiling a soup on the stove, and you boil it too vigorously, you'll get splatter shooting everywhere. The same thing will happen with metal, and that splatter will create roughness and deformation and lead to print failure. So that's what we had happen here. So next we took all these samples and we measured the thermal properties with flash diffusivity. So in flash diffusivity, we take our sample and we send a very brief pulse of radiation to the top surface. And then we measure the temperature response on the other side of the sample. And based on the time it takes for that thermal wave to penetrate the sample, we can determine the thermal diffusivity and thermal conductivity of the material. So these blue circles are the experimental temperature versus time. And the red curve is an analytical solution to that distribution. So this is just one sample that we did, but this just gives you an idea of how the measurement works. So next, sorry, skipped ahead too much. So this is a plot of thermal conductivity versus laser scan speed. And at too high a scan speed, so at 2000 millimeters per second, you might remember we had some porosity. And so it's natural that the thermal conductivity of that is lower. At slower scan rates near where there's very low porosity, the thermal conductivity was kind of plateaued here, just like the porosity was. And then kind of in between that, we see that the through plane conductivity here in blue decreased and was lower than the in plane conductivity. And the reason for this, when you're not printing an optimal process parameters, the laser melting doesn't fuse neighboring layers as well together. There's maybe more grain boundaries and defects at the interlayer connections, and so that lowers the through plane connectivity, more than the in plane connectivity. Next, we want to analyze the thermal properties versus porosity. So here's the same data presented versus porosity, and we can see that the porosity decrease explains a lot of the reduction in thermal conductivity, especially for these high porosity samples, but it doesn't fully explain the reduction in thermal conductivity. So that was somewhat mysterious. So why is it much lower than we'd expect from porosity? So we next did thermal conductivity mapping. So these are thermal conductivity maps that we made in the in-plane and through-plane directions. And just like we did with copper through tin, we tried to relate this to a microstructure. So we did electron backscatter diffraction to measure the orientation of different grains. And we thought maybe there'd be some relationship between the crystal orientation and the thermal conductivity map. But unfortunately, or well, doesn't matter. I mean, there was none. We also looked at elemental mapping, and we couldn't find a relationship between the thermal conductivity variation that we saw in the map and these microstructural properties. Well, one thing that we did observe, though, we did X-ray diffraction. Dr. Peters of Algae at University of Maryland did X-ray diffraction on these samples, and the intensity of the X-ray diffraction peaks are shown here in blue. This is a Rietveld scaling of these, and the thermal conductivity shown here in red follows a similar trend. So we thought this was interesting. We didn't quite know why this would be, but we thought this was interesting. And we next did transmission electron microscopy. So my colleague Guangwen Zhou and Xiaobo did transmission electron microscopy on this copper 3 tin sample. Here's the interface between two grains. This is high resolution TM. So the scale bar here is just 5 nanometers, incredibly small. And if we zoom in here inside the inside the stainless steel, did I accidentally say copper 310? Inside the stainless steel, you can see that the regions that are somewhat blurry inside the stainless steel. And this is actually indicating that there's some amorphous region inside the stainless steel. And we think that this amorphous region is leading to a reduction in X-ray diffraction intensity and also reducing the thermal conductivity of the stainless steel at those faster scan rates. So just to summarize here, we found that the thermal conductivity also varied with scan rate, with laser processing conditions, and that this matched the reduction in X-ray diffraction intensity. And we attribute this to some amorphous domains that were created inside the stainless steel. So our plans on this area going forward is to basically look at how we can use these thermal conductivity properties to print better materials and to also increase the thermal conductivity of selective laser melting parts. So I'd like to thank you for your attention. We talked about several different topics related to 3D printing onto silicon, and thank you for your attention. And I'd like to also acknowledge our funding and collaborators. And glad to take any questions you may have.
Thank you very much, Professor Schiffres. Definitely appreciate your time and presentation and walking us through the different areas and aspects to your research. So at this point, we'd like to open it up for questions.
Certainly.
So to our participants, please feel free to unmute yourself and ask the question or type it in the chat.
Hello, this is Mohammed. Thank you, Professor
Yes.
Schiffres, for such a great informative talk. So I do have a question regarding the temperature versus the laser power. So have you done any either experimental or estimation how much temperature do you have per specific power, laser power?
Yeah, that's a great question. So, are you talking about it with printing onto silicon or the metal printing process in general?
Yeah, in general.
Yeah. So actually, I have a postdoc who just joined my group several months ago, Fatima Rafsanjani, and she's been doing really great simulations of the laser melting process. I can maybe pull up a video if you're curious, but the physics are really complicated. There's surface tension flows from gradients in the gradients in the surface tension due to temperature, and there's also vaporization. There's pressures being applied from vaporization of the metals. It's a very interesting and complex process. We've done some very basic. We just started to dig into the simulation details of this.
Thank you.
Yeah, you're welcome. Yeah, I can maybe share some if people are interested. We just got a better computer to handle a larger volume. Right now, we just did a few, the very small region, just a millimeter or so, I guess, of printing due to computational limitations. But we just got a new computer that can hopefully build on that.
Thank you.
Yeah.
Professor Schiffres, this is Prabhu. I have a question about the first part of your presentation on printing on silicon. I want to know whether that technique could be used for other high performance semiconductor devices that are made out of gallium arsenide, for example, or even superconducting circuits, which is a completely another ball game. But I think those circuits make use of niobium and other superconducting materials. So do you think that this might be possible to be extended to other class of electronic materials in the coming time?
That's a great question, probably. I was actually just talking with somebody yesterday about printing on other materials. And they were asking about gallium arsenide. I was actually scared to touch it because worried about my student getting arsenic poisoning. But I haven't thought as much about gallium arsenide, but I've been thinking about gallium nitride or silicon carbide. And I think it should be possible. About superconductors, I haven't really given that any thought, but that's a very interesting idea. So with superconductors, is that transition to the superconductor very important to print the cooling fins, or I haven't researched that as a topic, but that seems like an interesting area to look at. It's a good idea.
Yeah. Okay. Yeah, that'll be interesting. Thank you.
Thank you, Dr. Barathan.
Prabhu, I'm a student here. I'm
a student. Okay. Okay.
Thank you.
It sounds like a PhD question.
Yeah, in the PhD program many years before I become a doctor.
So Scott, there is a question in the chat from Dr. Raghu Raman about how do you control the fabrication process?
That's a great question. So we do it all through software, actually. So we can, in the software, we could change the laser power and the speed at which the laser moves. So that's one set of controls. And then there's other controls that we can make as well. So we can let me see if I have if I can jump to the slide. There's a lot of settings inside the printer. I could talk for hours about all the settings that this EOS printer has. But one of the other ones, besides just the laser power and scan rate, another important one is every print layer, the laser scan direction will be rotated. So there are different settings for that, but that's to reduce thermal stresses from always melting in one direction. And then there are other settings as well. Like when you print a part, you could print the inside of the part and then melt the perimeter afterwards. There's an inner print setting and then an outer print setting. There are probably 100 different settings at least in the printer though. So I'm only scratching the surface. Some of them we had to ask, support for help with, figuring out what they actually do. But the machine has a ton of different settings.
Okay, great.
I don't know if that answered the question fully, but.
So why is there a sudden increase in the temperature, porosity gradient in that graph?
Oh, what's the porosity gradient?
Yes, sir. Yes, sir. This one.
Oh, what's causing it, or?
Yes, sir. There is a sudden increase from right from 0 to 5. Is there anything to specific to that?
Yeah, so that's a good question. So we're keeping the laser power fixed, and then we're changing the speed at which the laser is moving across the surface. So if we move it too fast, there won't be sufficient time to fully melt the whole layer and bond everything together. So there'll be these regions of incomplete fusion that'll occur. So we'll have porosity from this incomplete fusion of the metal. At lower scan rates, there are these little defects. It might be hard to see the little dots. These are basically keyhole defects. Basically, let me see if I can pull up a video of the melting process. But they're basically there's a little well that's in the print pool. Let me see if I can pull up a video real quick. Okay. So I'm going to share my screen here again if I can get to the setting. So this is a simulation. So here we have the powder. Can everybody see the video? I'm gonna hit play, but
yes.
It happened very quickly. So these are the metal powders, and they're resting on a substrate here. And so the laser comes in, and it's heating, and it creates a divot due to the pressure of the laser melting. Due to vaporization, it creates a little divot. If I pause it here, you can see that there's a little divot here in the print. This is because the melt pool is, the molten metal is getting basically blown by vaporization. The metal underneath the laser is boiling, and that's basically pushing the metal there down. It's kind of like if you blow in a bowl of soup, you'll have a little divot there. And so every once in a while, these divots collapse and trap some air inside the part.
Mm-hmm.
So I don't show the actual, I don't have a simulation that shows the collapse of this handy, but there have been some very large simulations that have been done on huge supercomputers, and they've shown how defects form in this process. I could pull something up. If you email me, I'd be glad to send you some additional information if you're curious. There's some papers.
Yes, sir. Thank you, sir.
By an author, Kairala. I can share them with you if you're interested. Just feel free to email me.
So Scott, if you don't mind, maybe we can paste your email address in the chat.
Oh yeah, sure, yeah.
Just to follow up with you, if that's okay. Okay.
Yeah, of course, yeah. I don't. Yeah, so yeah, so I just shot my email address. So
thank you. Any other questions? Again, feel free to unmute yourself or type it in the chat. Okay, if there are no questions, on behalf of Binghamton University and VIT, I would like to thank Professor Schiffres again for your time and for your presentation and contribution to this webinar series. And we are glad that this has inspired several questions and interest in getting copies of some of your publications, which is always nice. So thank you again, Scott, for your contribution. We definitely appreciate it. And with that, I would like to just.
Sorry, it somehow disconnected just now. I don't know what I clicked.
Oh, no problem. No problem. Yeah, thank you, Scott. Thank you. So
lucky that happened at the end of the talk.
Thank you. Yes, luckily. So I just would like to, before we conclude, I would like to let everyone know that next week we have a presentation from Professor Raja at VIT. Professor Raja will talk about improvement of surface integrity on additive manufacturing metallic structures. So we hope that many of you will be able to join us next week. Invite your students, invite your colleagues, scholars to attend and learn more, given the focus on additive manufacturing in the last 2 lectures or so. I think it gives us a good sequence of topics in different areas within the broad area of additive manufacturing and 3D printing. So I hope many of you will be able to join us. And as always, I will follow up with a recording of Professor Schiffres' lecture today and with the link to the registration for next week's presentation. As always, it's the same link. However, you know, you need to register every week because of the way the webinar series is structured. So thank you again for your participation. Have a nice evening if you are in India, and enjoy the rest of the day if you are here in the US or in Italy. Thank you, Professor Bruno, again for joining us. Thank you, everyone.
Thanks to you. Thanks to everybody. Bye-bye. Thank you.
Thanks.
Thanks.